Good evening. I'm David Ferriero, the Archivist of the United States, and it's a pleasure to welcome you here to the William G. McGowan Theater at the National Archives. Whether you're here in the room with us or participating through Facebook or YouTube, and a special welcome to our C-SPAN audience. I'm pleased you could join us for tonight's program, Small Steps and Giant Leaps, How Apollo 11 Shaped Our Understanding of Earth and Beyond. Tonight's program is presented in partnership with the American Geophysical Union, which is celebrating its 100th anniversary this year, and is made possible in part by the National Archives Foundation through the generous support of the Boeing Company. We thank them for their support. Starting tonight and for the next 4 days, we are commemorating the 50th anniversary of the historic flight of Apollo 11 and the first moon landing. Tomorrow night, July 18th, we will screen the recent celebrated documentary Apollo 11, crafted from newly discovered video and audio recordings here at the National Archives. Following the film, NASA's Chief Historian Bill Barry will moderate a discussion with Director Todd Douglas Miller, producer Thomas Peterson, and National Archives motion picture archivist Daniel Rooney. On Friday, July 19th, we will show two films in the afternoon. At noon, we will have Mare Tranquillitatis, episode 6 of the critically acclaimed 1998 HBO series From the Earth to the Moon, and at 3 p.m., we'll show Moonwalk 1, a 1970 NASA documentary. And finally, on Saturday, July 20th at 2 p.m., we'll screen the 2018 feature film First Man, starring Ryan Gosling as Neil Armstrong. Upstairs in the East Rotunda Gallery, be sure to see our special display of 4 documents that show the multitude of smaller steps and details that were necessary to the success of the Apollo 11 mission. The records include the flight profile, the entire 8 days of the mission, the plan for the hour that the lunar module landed on the moon, pages of moon landing transcript, and a card that details the itinerary the astronauts were to follow during their moonwalk. Those documents will be on display through August 7th. To keep informed about these events throughout the year, check our website, archives.gov, or sign up at the table outside the theater to get email updates. And you'll also find information about other National Archives programs and activities. And another way to get more involved with the National Archives is to become a member of the National Archives Foundation. The foundation supports all of our education and outreach activities. And now it's my pleasure to turn the program over to Christine Mcentee, the Executive Director and CEO of the American Geophysical Union. The AGU is a worldwide scientific community that advances the understanding of Earth and space through cooperation in research. She is the 3rd Executive Director in AGU's 100-year history. For over 25 years, she has made her mark as an association leader and innovator. In 2011, she was chosen for America's Top Women Mentoring Leaders, and in 2012, she was featured in the 100 Women Leaders in STEM. Ladies and gentlemen, please welcome Christine Mcentee.
Okay, thank you, David. On behalf of AGU and our 100,000 scientists that reside in 130 countries around the world, welcome to tonight's special event, Small Steps and Giant Leaps, How Apollo 11 Shaped Our Understanding of Earth and Beyond. We support Earth and space scientists and their collaborators so they can advance and communicate science and its power to ensure a sustainable future. We're proud to co-present this event this year in our centennial year as an organization. In 1919, when AGU was founded, the world was a very different place. However, despite the centuries' worth of change, the ability of Earth and space science to improve our society and the desire of scientists to provide that benefit to humanity has remained the same, as has the awe of discovery that all of us witnessed if we had a chance, as I did as a 14-year-old girl in a small town in western Pennsylvania, to watch the lunar landing on black and white TV. Earlier in the year, I was honored to interview geophysicist and NASA astronaut Dr. Drew Feistel, who most recently commanded Expedition 5556 on the International Space Station. During our conversation, he spoke about the resonance of the Apollo 11 mission for him personally and for humanity. He also drove home the point that the lion's share of the research done on the first lunar landing was geoscience, including the collection of lunar samples, the deployment of scientific instruments, and the collection of core samples on the lunar surface. Geoscience, he said, will continue to play a pivotal role in the future lunar or other planetary missions. He also spoke about how over the course of his 197 days in space on his latest mission, he saw the changes that the Earth is having in its climate, how floods affect our planet, and other geophysical phenomena are impacting the Earth's surface. He also experienced what astronauts have dubbed the overview effect. When viewing the Earth from space, many astronauts see firsthand the fragility of our global environment and how we all are protected and nourished by our planet's thin atmosphere. From this vantage point, boundaries between nations disappear, and the issues that separate people are viewed as less important. What does become clear is the need to create a more unified global society, one that works to protect all of the inhabitants of this pale blue dot that we call our home. During times of uncertainty and change to Earth's climate and the scientific enterprise, all of us, particularly the scientific community, must join together to address these concerns. Like all of us and those who were part of either witnessing or being on the Apollo 11's mission, we have to be creative and passionate, committed and determined. We must advance research and do so with the integrity and transparency that is the foundation of scientific discovery. I am now proud to introduce AGU's president, Dr. Robin Bell. Robin has been a member of AGU for more than 30 years and became president-elect in 2017. She is a past president of our cryosphere section and was elected as an AGU fellow in 2011. She received her undergraduate degree in geology from Middlebury College in Vermont and her PhD in geophysics from Columbia University. Since completing her doctorate, Robin has led research at the Lamont-Doherty Earth Observatory on ice sheets, tectonics, rivers, and mid-ocean ridges. Please join me in welcoming Dr. Robin Bell.
Well, welcome. I'm very excited. Anybody who's ever come within about 10 feet of me realizes I'm like a natural geek. And when I realized we were going to have this wonderful event, first I thought I could just I began to think, where was I? It's one of my favorite questions to ask anybody. Where were you when when the Apollo 11 landed? I was on Aunt Mabel's couch was kind of the same color of these chairs, was red but naugahyde, and everybody in the little community was jammed into the room because she had the only TV in the community. So we had about 45 people jammed into the room. But I decided that I should actually look a little deeper than just the couch into what I consider sort of my lunar legacy. So I began to poke around at my institution because it turns out Lamont, Columbia University, had a lot to do with the geophysics of the Apollo mission. And I knew there was a gravity meter I'd been tripping over my entire life. It's out, I shouldn't tell you. I went looking for it. So I went first to the attic of Lamont Hall, the same place they mapped the bottom of the ocean floor. And then wasn't there. I found Apollo 11 slides and pictures, but no gravity meter. So next I checked all the closets in the mansion, no gravity meter. Then I got really brave and I went to the cellar of the oceanography building, and yes, there were jars of jellyfish in the cellar. I knew those were not from the moon. I knew it. But I kept on looking, and then I finally opened the door, and there it was, under a net. I don't know why it was under a net, but there was the mock gravity meter that you can actually find pictures of astronauts training on it. It went on the back of the vehicle. But then I remember so that's out on the table if you want to see it. I brought it down on Amtrak. I think it's the first time a lunar gravity meter's had a trip on Amtrak. But then I decided I wasn't going to give up, because I remember that Mark Langseth, who was on my committee, had conveyed one of these very important lessons in science: is you don't give up, because he'd wanted to make heat flow measurements on the moon. And when he first tried, something happened to the flight. It was Apollo 13, okay? Apollo 14, the drill stuck, and they only got one measurement. Apollo 16, it's the first time there was a swear and apology from the astronauts back to a scientist, because something bad happened. In Marcus's obituary, it says a misstep. Well, they tripped over it and pulled the wire. But Marcus stuck with it. So by Apollo 17, the astronauts are on the moon, and they're actually joking about how not to trip over the heat flow measurement. So what I walked away from Marcus's lesson was, don't give up, that you can be really patient and you can get what you want. So we went to the cellar again. This time I took colleagues. I didn't want to be down there in the jellyfish by myself. And what did we find? We found high up in some of the piles of boxes, we actually found the heat flow instruments. So it's just been wonderful. I also learned the stories of the measurements they made of how the velocity of moon rocks isn't that different than the velocity of cheese, published in Science magazine, 1970. So it just shows that scientists can be very patient, recover from disasters, and have a sense of humor. So I hope you're going to enjoy the program as much as I'm looking forward to tonight. We're going to learn a lot. There's some amazing people back there we're going to learn from. And in my role as president of AGU, I realize now, having watched the eyes of my cohorts when I went back on trip to the cellar number 2, just how inspiring all this work is to the next generation, that just being able to hear the stories, hear where their parents were when the moon landing happened, actually just lights up their eyes and gets people inspired to work on science on this planet and on other planets. So now I'm very pleased to introduce Dr. Jim Green, who's NASA's chief scientist. He received his PhD in space physics from the University of Iowa, and then worked at NASA's Marshall Space Flight Center, where he developed and managed space physics analysis network. Before becoming NASA's chief scientist, he was a director of the planetary science at NASA headquarters, where he saw missions including the New Horizons flyby of Pluto, the Juno spacecraft flight to Jupiter, and one of people's favorites, the landing of the Curiosity rover on Mars. So we're very lucky to have him as the moderator of the panel tonight. So please join me in welcoming Dr. Jim Green.
Good evening. Wow, I'm glad the rain didn't stop you from coming, because we're going to have an exciting time tonight. We're going to talk about Apollo 11. We're going to talk about its legacy. We're going to talk about the science that we learned and how it sprung us forward into discovering many more things about the moon and the origin and evolution of the solar system. This is going to be a really exciting time. We'll also talk about the future of lunar exploration. So, without further ado, I want to mention a couple important things. Everyone should have some cards. If you have cards in the audience, these are important because you can write questions down. So please write your questions. As they come up, I find that's usually the best way to go. Hang on to them, and then what we'll do at the end is we will pass them down to the end and go through as many as we can. Now, in addition to the audience that's here, we also have remote viewers. And so for them, let me read on Twitter what hashtag they should send their questions to. So that's hashtag ApolloQA and hashtag AGU100, okay? So for those online, please get ready, get your questions, and then we will try to get to as many of them as possible. So tonight, we're going to have a moderated panel. I am just delighted to have been asked to moderate the panel. We have some of the best planetary scientists in the world, okay? Those that have worked with even Apollo 11 data and all the way to LRO, which is our Lunar Reconnaissance Orbiter that's there now. So without further ado, let me begin some introductions. First, I would like to invite Sonia Tikoo onto the stage. Sonia is the Assistant Professor of Geophysics at Stanford University. Sonia. Next is Dr. Sean Solomon. Sean is the Director of Lamont-Doherty Earth Observatory. Sean. We also have Heather Meyer. Now, Heather is a postdoc fellow at the Lunar and Planetary Institute in Houston, Texas. Heather. And last but not least, Stephen Hauck. And Stephen is the professor and chair of Earth, Environmental, and Planetary Sciences at Case Western Reserve University. Stephen. So we're going to start out by talking about the legacy of Apollo and what it meant to the country going back now 50 years. We're going back in the Wayback Machine. And out of this panel, two people actually observed the landing, and that was Sean. Much more as a working scientist, and then as a young high school student, Jim Green here. And so there are some fond memories, I'm sure. So I'm going to ask Sean, take us back to that lunar landing. What was the feeling of the science community at that time? What were they excited about?
I hope some of you will remember the Apollo 11 landing. But I was a graduate student in geophysics. I was at MIT. And the world had been following the Apollo program and the lead up to it. And so we had the anniversary of the launch of Apollo yesterday, Apollo 11, I should say, and this Saturday we'll have the anniversary of the landing. That evening, July 20th, 1969, late afternoon was the landing. And I would say that there were probably billions of people around the world who were watching that event all over the globe. And it brought humanity together to look at a technological achievement in a largely apolitical way. And it really was a marvel of technology that less than 8 years after President Kennedy announced in his speech in Houston in early 1961, challenging the country to go to the moon before the end of the decade, to send humans to the moon and bring them back safely, that we did that. And 1961 was such an early phase of the space program. The first humans had orbited the planet. It was only 4 years after Sputnik. And yet, within 8 years, we could carry out Apollo 11. It's really extraordinary. It took an agency that had the backing of the country, had resources, and had some really amazing engineers who figured out some very challenging problems. So one of the things that the scientific community realized was that they were witnessing a remarkable event in history and a remarkable technical achievement. But scientifically, the Apollo 11 mission was enormously important to our perspective of how our planet fits into the solar system and what the early history of the solar system was like. And I can't understate the importance of the Apollo 11 mission in particular for bringing back lunar rocks, lunar soils, lunar core samples into the best Earth laboratories, where the most sophisticated instrumentation, many of the instruments having been purchased by NASA specifically for the Apollo program, were ready to look at the lunar samples. And we immediately learned that the moon is very ancient. We immediately learned that all the maria on the moon are volcanic. And we immediately learned through a great leap of logic on the part of two very distinguished scientists that the highlands of the moon, the bright areas, were the product of an early stage in lunar history when the entire outer part of the planet was molten and the crust formed as a result of cooling of a magma ocean. And all of that came from the Apollo 11 mission. And it led to an explosion of understanding of the early history of the planetary system, a part of the system of our planet that's not preserved in our rock record. So I'm not sure I realized all that as a graduate student sitting in front of the television and listening to Walter Cronkite, but that's what happened. And it didn't take long before the scientific community realized what a watershed event it was.
Yeah, indeed. You know, we're celebrating the 50th anniversary, and I think a lot of people in the general public think of it as human exploration, but science was there from the very beginning. When I watched it, one of the startling things that I saw was when Neil walked out of the capsule, before he walked down and said his famous lines, is he looked around and he saw how the lunar limb was sitting on the surface and how deep the legs might have been crushing into the regolith. And there was some debates on how thick that might be. And although we'd landed on the moon by the surveyors, you don't know if it's piling up in certain areas. So he was right off the bat talking science. And that was to me, was just pretty spectacular. Well, what science experiments did, Sean, you get involved in? What did we put down on the moon for Apollo 11?
Apollo 11 was the first, of course, of the landed spacecraft, and there were a total of 6 that landed successfully. And it wasn't the most ambitious by far in the experiments that it brought to the surface. But one of the opportunities provided by the Apollo missions was the opportunity to do seismology, to study natural tectonic events and the impacts of meteoroids on the surface of the moon using seismometers, analogous to what terrestrial geophysicists had been doing for 3/4 of a century, studying earthquakes all around the world and using the earthquake waves to learn about the interior structure of the Earth. And so scientists at my institution and my current institution and a few other institutions got together and sent a seismic system on Apollo, including Apollo 11. But for reasons of cost, for reasons of schedule, the very first passive seismic experiment carried by Apollo 11 did not have a long-lived power source, so it only lasted 3 weeks. And it produced signals that the very best seismologists in the world could not understand. So for 3 weeks, there were seismic signals being recorded by the seismic system on the lunar surface. Then the power ran out, and the signal stopped. And really distinguished seismologists, Morris Ewing, Frank Press, Gary Latham, others, who had been working on lunar seismology and thinking about it for years prior to the mission, didn't know what they had in the way of the signals. And shown on the screen there is really an explanation. The top 4 traces are lunar seismograms, and the bottom trace in red is an Earth seismogram. And so the seismologists had taken seismometers to the moon with the mindset that they would see signals like you see on Earth. And they saw signals that looked very different, that were full of high-frequency energy, that didn't have distinct arriving phases, and that rang on for tens of minutes or an hour. It was said that the moon rang like a bell. And the Apollo 11 signals were nobody figured out what they were. It took Apollo 12. And the difference was the Apollo 12 astronauts landed in a different place. They took another seismometer system. It had long-lived power sources. Then they left the moon again. But the seismologists had asked NASA for permission when the astronauts docked with a command module in lunar orbit and didn't need the ascent vehicle anymore to send the ascent vehicle back down to the moon where it would crash. But it would crash and create seismic waves. And it would crash at a known place at a known time. And so for the first time, they had a seismic source, the characteristics of which they knew. They knew the energy, the time, the location. And it produced seismograms like the ones they'd seen on Apollo 11. And it was an aha moment, they said. This is what seismograms look like on the moon. But it took another experiment. It took the cooperation of the flight folks at NASA to recreate an event so that we could understand how different the moon is from the Earth. And it's different for a variety of technical reasons. It's different because the outer tens of kilometers are fractured and broken up. And the moon is extraordinarily dry, and so seismic waves go on for hours instead of minutes. And none of that had been anticipated before the Apollo mission. So the lesson was, if you take a terrestrial experiment to a new planetary body, you really have to think out of the box sometimes to interpret what you find.
Yeah, indeed. These are fabulous sets of data, and so we call them wiggle plots. So if you're really excited about these, you have a scientific career, please see me after the lecture. So, well, you know, they also collected a variety of samples. They did a fabulous job. They actually had about 50 pounds worth of samples that Apollo 11 crew brought back. So Sonia, why do we need those samples? What can we learn from those?
Yeah, so the Apollo samples are not just a bunch of souvenirs, even though they are really cool, but they represent this incredible treasure trove of knowledge about processes occurring in the early solar system, not just how the Earth and Moon formed, but also the incredible bombardment of giant impacts that were occurring in the first billion years or so after the solar system initially formed. And so, you know, what's great about getting whole rock samples from the moon on these crewed missions is that we can bring them back to Earth and cut them up into 100 pieces and send them to 100 different labs and do 100 different experiments on the best equipment possible, and as Sean pointed out earlier. And it's because of this that we can address a much wider diversity of science questions than you can with, say, a few instruments that you could put on a rover. And you can have a higher diversity of viewpoints of different scientists with different perspectives addressing those questions. And so from that perspective, getting actual rock samples from the moon is integral. And we have lunar meteorites. You know, moon rocks fall to Earth all the time. But what's great about the Apollo samples is we know exactly where they came from. We know exactly what geology they represent. And so thanks to these samples, we've learned some really incredible things. We've learned that the Earth and the moon are geochemically very similar to each other, and that in some sense we have a common origin. And this led to this giant impact hypothesis, which you may have heard of, that the moon formed by the impact of, say, a Mars-sized body into the proto-Earth, and then all this debris that was launched from the Earth recoalesced and formed the moon. And we wouldn't know any of this without the samples. We can date rock samples that are basically glasses from impacts hitting the lunar surface and melting rocks and recrystallizing it, and we can radiometrically date them and figure out when those impacts happened. We can learn that the first billion years of our solar system's history was chaotic. And, you know, we know about the impact that killed the dinosaurs 66 million years ago. In the first 2 billion years of Earth history, stuff that big or bigger happened 300 times based on the scaling laws that we developed from studying the moon. So that is the power of lunar samples from the Apollo missions. And so it is fantastic that we get to work with them.
Yeah, in fact, over all those 6 Apollo missions, we brought back about 840 pounds worth of lunar material. And as it came back, the first thing we did was we set aside about 25%, not to be looked at. And it's done that way because as we learn things about how we analyze the current material we have in our hands, we can then approach the new material that way. But over these last 50 years, our ability in the laboratory to look inside these rocks with CT scans and the individual atoms and getting the isotopes and all the complexity that these samples provide us is now becoming well in hand. And so this year we're opening some brand new samples that we've never opened before. Well, we had the panelists think about some of the great images from the Apollo program. And we've asked them to give us those, and let's talk about these. So here's our first one, and this comes from Apollo 8. This was yours, Sean. What do you think? What did you see? What did you feel like when you saw that?
Those of you who read the Washington Post should have seen a story yesterday on this very image. I think it's one of the most compelling images to come out of the Apollo program. Apollo 8, you may remember, was before any lunar landing, but sent the first astronauts to loop around the moon before they came back. The astronauts were James Lovell, Frank Borman, and William Anders. And when the spacecraft came from out of the shadow side of the moon to view the Earth rising above the horizon, Anders took this famous image, Earthrise. And Borman was quoted in the Post yesterday as saying, all three of the astronauts just were awestruck by this image, and because of the beauty of the home planet, because it was almost the only color in the sky, because you could see the fragility of Earth's atmosphere, and yet we rely on that with every breath we take. You could see land, you could see the oceans, you could see that from space there are no political boundaries. And the contrast with the completely arid and desolate, though beautiful, moon was more striking than really had been appreciated up to that moment. And in the 50 years since then, the magnificence of this space view of Earth and the realization that the changes that mankind has imparted to our atmosphere and our oceans have made it a less habitable place than it was 50 years ago. Just underscores how precious this, and in our solar system, fully unique this planet is. So it took the venturing of humans into space to look back from another airless ancient surface and give new appreciation to our home.
Yeah, to me, when walking around the newsstands, just about every magazine that could grab a hold of this and had it. I remember Life, which was a huge magazine, very popular, had it front and center, and it was just really awe-inspiring. So they weren't the only three that were inspired. Iconic image, one of the great images of the last century. Next one, please.
Oh, okay. All right, this is one of my favorite photos. It's from Apollo 15, actually, and it's a picture of Commander Dave Scott kind of collecting samples on the lunar surface. And I'm a sample scientist. This is like my bread and butter. And so you really get a sense of how they were going about it in this photo. So you see that he has a bag in his left hand that already has a rock in it. So there's a sample bag, and they put these little tiny rocks that they picked up off the ground, into them. He's messing around with this larger rock in the center of the image, and on top of it is this funny stick-looking tripod thing, right? It's called a gnomon, and it creates a shadow. And what was cool about it was when you're on the moon, you don't have a compass that can tell you which way is north, south, east, or west. If people on Earth wanted to reconstruct what direction they were studying, they had to use the sunlight angle that was cast on this stick at the top of the tripod onto the ground. And it's the sunlight angle coupled with the time, and they could figure out what direction was what. And so this photo is amazing because it gets you a sense of just how they were going about their business on the surface. You know, you have the footprints in the soil, you have the spacesuit, you have the sample bags, you have the whole thing. But I have to say my favorite part of this image, unfortunately, got cut off. Because if you actually were to like tilt upward at the top, in Dave Scott's helmet, you have the best selfie of all time because there's a reflection of the other astronaut's spacesuit and camera in the image. And yeah, so it just goes to show you that Instagram is not a modern phenomenon. They totally were rulers at selfie taking even during the Apollo era.
So these were really bulky suits, and it's very hard to be able to, in these bulky suits, be able to pick up the material on the ground. So they had a variety of things that they would use to pick them up. In fact, one of the astronauts wanted to pick up this very heavy rock and knew that it might take him down if he picked it up. So he actually put his leg up against it, and then with one of the rods that they had with a fence on the thing that picked up rocks, he just rolled it up his leg and then threw it in the box. But indeed, we have to, when we look at our rocks in the archive today, we have a little orientation cube which talks about where the sun was during that time period when the rock was collected. So we try to maintain all that data. Yeah. Next slide, please.
I think this one was mine.
Yep.
So this is an image that I think captures a lot of what Apollo 11 astronauts Armstrong and Aldrin were doing when they were on the surface. So in the foreground, we see that's actually the seismometer that Sean was talking about earlier that was powered, solar powered, even back in 1969. And that they were able to install quite quickly, whereas the ones that came on later missions took them a bit longer, and those also lasted a lot longer. On the top of it, you see sort of a white stick. That's actually the antenna that allowed us to get data back from the moon to the Earth. Behind that, you can see sort of where that white stick is. You can see it looks like sort of a white triangle. This is an experiment that's still operating today from Apollo on the surface of the moon. It's a lunar laser retroreflector, and its purpose is to do a better job of reflecting laser light back from the surface of the moon. And this was an ingenious experiment because it required no power. It just had to sit there. And then all of the technological advances happened here on Earth as our lasers got better, as our telescopes got better. And we use this, scientists use this to measure the rotation of the moon, the distance of the moon, and the major things that we learn about it is what does the inside of the moon look like? How does it respond to the tidal stresses that it receives from the Earth? And that tells us about what the deep interior of the moon is like. And so this is an experiment that has been going on for 50 years. And then in the background, we can see other iconic parts of this Apollo 11 image. We can see the flag that was in place. We see the lander. And then in the far distance, we can actually see the television camera that they used to provide the first interplanetary television show.
Yeah, that's right. Next one, please.
That's me. Okay, so Sean took my favorite image. So we'll have to do with this boot print. So many of you have probably seen this image before, but just for context, I'm a remote sensing specialist, so I work on data from orbit. And most of what we do from orbit depends, what we interpret and how we see it depends entirely on the properties of the surface. And so one of the things Apollo did was teach us a little bit about the properties of the regolith, which is just the topsoil essentially, and those properties so that we could derive meaningful information from orbit. And so this boot print may not look like much, but if you're a Sherlock Holmes fan, there's actually quite a lot of information here So for example, like I said, regolith is the uppermost part of the surface. It's like dirt, right? And the fact that you have this imprint, this rather large imprint in the surface, indicates that there had to be some space between the grains of dirt in order for it to compress. And so that compressibility, that empty space, we call that porosity. And so porosity just changes depending on where you are, but in this location, there's at least somewhat porous. And so that actually affects the way we see light that's reflected back from that surface. So that's actually critically important for making sure that we're interpreting things correctly when we're looking back down.
Indeed.
This is the same, so I had to go for 2 because he took my favorite.
That's good. That's good.
So,
Well, that's what Neil was looking at.
yeah, so as Jim mentioned, the foot pads touched down and they had these little rods that stuck into the regolith. And they didn't sink down by too much, a couple inches, not too much. But it was telling us that the uppermost part of the soil was not as porous as we expected, but still fairly porous such that the lunar module could sink just a little bit. But it was perfectly sufficient to support the weight of the astronauts. Nobody got stuck, But properties like this are really important, not only for orbital stuff, but for ground operations. So you need to know that you can move around on a surface, right? We would not send rovers if we thought it would get stuck in the sand, right? And so things like this are critical considerations that were beautifully demonstrated by Apollo 11. And we got a kind of a surprise that it was not as porous as we thought. They didn't sink as far as we thought they would. So yeah.
Well, us scientists, really delve into things and we really get excited about a variety of things that maybe people think are minutia. But there can be some really exciting discoveries. So what are some of those things that you think the general public would be interested in knowing that you really got excited about? So let me open it up to the panel.
Well, I could talk about magnetism now.
Yeah?
Yeah, sure.
Does
Yes.
the moon have a magnetic field?
Yeah, so the
know.
moon used to be magnetic. You probably know that the Earth has a magnetic field. It's invisible, but we're sitting in it. And it tells us where north is if we use a compass. But the moon actually used to have a magnetic field too. And you're probably wondering, why does this matter at all? So that's what I'm going to explain. So if we go to the image of the moon and its magnetic field, yay, there it is. So this is an artist's conception of the magnetic field that used to be on the moon billions of years ago. And it has to be an artist's conception for several reasons. One, we can't see inside the planet, and 2, magnetic fields are invisible. So therefore, we need some help from this artist named Hernan Cañelas, who is amazing. And so magnetic fields, the way I think of them, they're almost like the heartbeat of a planetary body. They are this invisible but detectable signal that tells you that there is some activity going on inside at the core. And so in the case of magnetism, the process that is occurring is organized motion of molten metal, hot liquid iron at the center of the planetary body. And it's moving around in such an organized way that it can actually generate a magnetic field. And so it tells you that the planet is alive and that it's cooling down. That motion is driven by thermal convection inside of the core of the planetary body. And so in some sense, it's a signal that the moon was active. And of course, what's funny about lunar magnetism is we did not learn much about it from the initial landing at the Apollo 11 site because they neglected to bring a magnetometer on that mission. But we fixed that in Apollo 12. All right, so if you go to the next image, there were 2. There's one of that one, okay. Yeah, so the image on the left that you see at the end of that rope or cord is this little box-looking thing with 3 prongs coming out of it by the astronaut, and that is a magnetometer that they took to the moon on Apollo 12. Now, you have a magnetometer inside your cell phone now. All smartphones have them, so this is just a testament to how the technology has changed over time. But what they were able to do was they were able to measure the field at the surface of the moon. And what they found was it was 1,000 times weaker than the Earth's magnetic field is right now, but it also wasn't zero. Okay, so why is that significant? It tells us that the moon was magnetized at some point. There was something there, which means that there probably was a core inside the moon that might have had a magnetic field generated from it at some point in the past. And so magnetism was sort of a weird, like circumspect way of looking at this problem, because from the laser ranging data from seismics, it actually wasn't obvious that the moon has a core. But if you can detect a magnetic field on the moon or show that it had one in the past, you can say, oh, this is the internal structure of the moon, and we know for sure that it had one. So the surface measurements were a hint of that, but what really nailed it was studying the magnetism that was recorded in Apollo samples from the time that they initially formed billions of years ago. So that's the picture on the right. This is also Apollo 12. But this is an astronaut picking up, or about to pick up, a moon rock with some tongs. And so what they were able to do is once these samples were brought back to Earth, they were sent to labs that study Paleo Magnetism. So usually when I say that, people are like, what, dinosaurs are magnetic? No, not paleontology.
At least their personalities are.
Yes. Thank you. Yeah, so paleo just means old, and magnetism is magnetism. So what we can do is we can stick a rock in a magnetometer. We can figure out whether it is magnetized. Rocks acquire magnetism when they form, and it records it and preserves it for pretty much all of its history after that. And so what the Apollo era paleomagnetists found was that the moon used to have, it seemed like the moon used to have a magnetic field or that imprinted magnetism in these rocks, prior to 3.5 billion years ago, and that it was at that time period, it was as strong as the Earth's magnetic field is today, which is surprising for a small body like the moon, because small body, small core, you're farther away from the core, it's not going to have such a big field. But it did, and so that was a huge mystery. And what actually persisted at the end of the Apollo era was people weren't sure whether the field was actually from the inside of the moon or not. There were all these other hypotheses that giant impacts can create plasmas, and that moving around generates magnetic fields, and that contaminates the rocks and all of that. So we kept ourselves busy for 50 years. And we came up with all these tests to show whether the rocks actually recorded an internal magnetic field generated by the moon or these other exotic, field sources. And what we found is that the moon actually did generate a field. And it didn't just last till 3.5 billion years ago. It actually lasted past 2.5 billion years ago. So we had a field on the moon for at least 2 billion years, which is much longer than people conceived of at the time. So it tells us that the moon was alive and active.
Yeah, very surprising. So you learn that planets evolve over time. I mean,
Yeah.
you'd go back 2 or 3 billion years and look at the moon, it'd be a very different object.
Yeah,
Very
totally
exciting.
different.
Very exciting.
Yeah.
What else? Yeah, Sean.
With Brendan's help, we've gone past the slide that I inserted in this group twice now.
You better talk about it.
I better talk about it. So this is a little bit like the case of the dog that didn't bark in the night. During and shortly after the Apollo missions, it should be said, NASA was very active at sending robotic spacecraft to other planetary bodies in the solar system. And in very rapid succession, we had been sending spacecraft to Mars and Venus and Mercury and Jupiter and Saturn in the early 70s. And it was only 16 months after the last Apollo mission that the very first spacecraft viewed the planet Mercury at a close range for the first time, Mariner 10. And Mariner 10 showed that Mercury outwardly looks a lot like the moon. It's got a heavily cratered surface like the moon. It's an airless body like the moon. It has plains, which we've since learned are volcanic, like the lunar Marea. But what Mercury has that the moon did not, and is illustrated by these two images from a later mission, is that Mercury is crisscrossed by huge faults that accommodate horizontal shortening of the crust. They're the kinds of faults that underlie the great mountain ranges on Earth that also are the kinds of faults that accommodate subduction on Earth and give rise to the very largest earthquakes on our planet, the very largest tsunamis. And these kinds of faults are seen throughout the planet Mercury. And the interpretation of the Mariner 10 team was that Mercury shrank, that it contracted as a planet over the course of its history because it cooled so much that the amount of contraction was visible in the deformational features that were preserved at the surface. Now, Mercury is only a little bit larger in diameter than the Moon, but the Moon does not have this global pattern of great faults that accommodate horizontal shortening. So the combination of the Mariner 10 results and the lunar imaging got me interested in the question of why Mercury contracted enough to produce all these faults, and the Moon, over its history, did not contract enough to produce a comparable pattern. And that speaks to the thermal history. It speaks to the history of the core that Sonia was just talking about. This particular question got me actively involved in lunar
What
work.
else that the public may not know about these discoveries?
So I think one of the things that may not be well understood is that the astronauts in orbit were doing science. It wasn't just...
It's fine. Go ahead.
There you go.
I'm sure we'll talk about different aspects. So on board those, the command modules that were in orbit, there were scientific instruments. And so, and some that became precursors of things that were really important that we did later in space exploration, and in some cases, exploration of our own planet. For example, on Apollo 17, there was a radar which could see beneath the surface. And so we were using radar to understand what was the depth of the regolith, what was the depth of the rock from orbit. It's the same kind of technology that we use here on Earth to understand how deep are the ice sheets in Greenland and Antarctica. There was a laser altimeter that tells us the topography of the surface. And I think one of the ones that I come back to a lot because when I was in graduate school, one of the scientists, Larry Haskin, who was a geochemist and a petrologist who worked in Apollo missions, he was interested in studying the gamma ray spectrometer, which could measure certain radioactive elements emanated from the surface. And there was this particular one, thorium, which was seen. So the Apollo command modules went around the equator, but they collected some data that suggested that there was sort of these hotspots of thorium. And by looking at the lunar samples, they had a suggestion that it came from this large and one of the last large impacts, Imbrium. And then later, when the Clementine spacecraft, and Lunar Prospector went there and was able to map the entire planet, they were able to see that their hypothesis, that the distribution of this one element that we say on the surface was largely attributed to a single impact that happened early in the planet's history.
Throwing material
all over the
place,
planet.
Right? Massive impacts. So the Moon took one for Earth that day,
Yes,
as
it
it
did.
did. Heather.
Kind of works like that, yeah. Large impacts are my specialty, so it's amusing for me. Yeah, no, he covered what I was going to talk about, but the important thing, one of the important things for what I do at least, and that was sort of drilled into me, is how important the samples were for orbital remote sensing. You know, the J missions in Apollo, so 15, 16, 17, because they had this instrument package where they could do really great orbital science and then tie it directly to the areas that we had sampled, meant that we could extrapolate to other areas. So we weren't limited to just the Apollo sites. We could actually look at other areas and say, hey, this looks exactly like we saw at the other Apollo site. We know what that is. And that is sort of the crux of remote sensing, you know, even on Earth and for every other planet, is that you can only tie it to things you know. And so getting the samples, those are the key. And for what I do, I mean, the samples, I don't know if you guys know this, I'm going to sound so cheesy, I'm sorry. But the rocks are, the moon is sort of our archive, right? Like the history is hidden in the rocks. And so we need to get those samples, not just for the chemistry, but for the ages. For example, with the large impacts, right? We use the relationships of the large impacts and the ages that we know, or think we know.
Yep.
We use that to determine the global stratigraphy and to say, okay, I know that area is approximately 3 billion years old, right? That whole system of connecting the sample ages to the stuff we see on the surface is extrapolated to all the other planets, all the other solid surfaces of the solar system. And so the information we have from Apollo is the basis for all of that. And it's relatively few data points. It's enough to get some good information, but we really need more. But it's a spectacular foundation. And so I think the tying the remote sensing to samples is far more important than people tend to think.
Well, indeed, this really brings up another little segment I'd like to do quickly, since we're running out of time, and that is after the Apollo program, everybody thought we took a hiatus. And we did a little bit from our robotic instruments, but in the 90s, we started getting back to the moon. And we had a whole series of missions, and we've learned an enormous amount by them. So what are some of your favorite discoveries from some of our more recent lunar missions? Stephen, let's start with you.
So I think one of the more exciting pieces of information that we've learned, particularly since Apollo, has to do with the discovery of ice at the lunar poles. So we have this, as the astronauts saw, and as Sean was talking about, our understanding of the lunar rocks. They're very dry. We don't see evidence of water, or at least not then, on the surface.
We thought the moon was bone dry. We called it bone dry for a couple decades.
Exactly. But then with later orbital missions, we were able to start to peer into pieces of real estate near the North and South Pole. And because of the way that the moon rotates, these are places inside these holes that basically never see sunlight.
Yeah, and so therefore the water remains frozen.
Yes.
Yeah, Heather, quickly.
Right for the picking. I forgot now what I was
Well,
gonna say.
LRO. The more,
yes. Right.
Yeah,
so,
the top.
We had some tantalizing hints from Apollo based on orbital imagery that there were some sort of weird volcanic things on the surface. And we call them irregular mare patches because we think they're similar to the mare in terms of composition. But they're really weird looking, and I wish I had included a picture. Anyway, so now we know based on LRO data that there are tons of them. And the reason these are interesting is because it suggests that the moon's volcanic history actually lasted a lot longer than we thought it did. And it's even possible that some of these things formed in the last billion years or less. And for a geologist, that's like yesterday, That's very fresh. And no one thought that lunar volcanism lasted that long and that it could because, like Sonia said, we thought it was dead, right? And so we have these hints that we now can go and investigate, and the irregular mare patches are one of the ones that we still don't know the answer, how they formed or how old they are.
This may anticipate another question you're going to ask, but I would say that one of the surprising things we have continued to learn about is how incompletely we understand the origin of the moon. We went to the moon 50 years ago saying, we know 3 ideas for how the moon formed, right? It was a sister planet of the Earth. It was ejected from the Earth by a rapidly spinning body. I've forgotten the third.
No, the lunar magma ocean, with the...
It doesn't matter. Capture. The third one at the time was capture of another body early on by Earth. And all of them were dynamically implausible, but those were the best ideas we had, and we thought that the Apollo missions would allow us to select one. And it did not. It said, these are all really bad ideas.
But we've got a top idea that we've hung on to now for a couple decades.
Yes, it was post-Apollo.
Yeah.
It took the scientific community more than 10 years to coalesce behind the hypothesis that the moon was born, this was mentioned earlier, as the aggregation of material thrown out from a giant impact of a Mars-sized object or something like the Mars-sized object that hit the Earth. what has challenged us in the 35 years since that hypothesis became generally accepted is that the deeper we study the chemical and particularly isotopic similarities of Earth and lunar material, the more difficult it is to understand this giant impact hypothesis.
Yeah. There's some twists and turns left there.
This was worked out several decades ago through the isotopes of oxygen, which were remarkably similar in the Earth and the Moon, but are different in most meteorites. They're different in Martian meteorites. And so if the Earth was hit by a Mars-sized object, surely it would be a remarkable coincidence for that impactor to start out with the same composition of the Earth. So why should the Moon, which is a mix of the target and the impactor, end up with an isotopic system that our ability to measure it is the same as the Earth? And in the last few years, we've gone down other isotopic systems with other elements and shown a similar remarkable coincidence, silicon, others. And we still don't understand it. The traditional dynamical models for throwing out ejecta from a giant impact, accreting a portion of that ejecta beyond the Roche limit into a satellite would produce a body that is different from the Earth in ways that the Moon is not different. So 50 years after the Apollo mission, we're still chasing the question, why do we have a Moon?
That's how science progresses, and then that allows us to take the next step of figuring out what the next set of measurements we need. So what I would like to have happen while we continue on discussing is the cards come to the end of the aisle. Perhaps most of them have then started to collect. And those online, using the appropriate hashtags, please submit your questions. And so let's just in the last minute before the questions come to me, and we can start the question and answer period. And they're already here. Wow, that was fast. That's great. All right. So we have we unfortunately can't answer all the questions, but we are going to be able to answer many of them and have them online at the AGU website. Okay, so a question from the audience is, should we directly challenge people who deny the moon landings ever took place? And what is the most effective way of doing that? Okay. Well, let me go ahead and start. The Lunar Reconnaissance Orbiter right now is orbiting the Moon, was launched 10 years ago, and is a very healthy spacecraft, and it is doing a marvelous job mapping the Moon to high resolution. If this table sat on the Moon, it would see it. And so consequently, we see these Apollo sites. We see the lunar limb takeoff platform. We see where the astronauts walked. We see where they deployed the instruments. We see their backpacks that they threw off their back before they walked into the limb to then leave the Moon. We see the lunar rover vehicle. So we can easily show those images, talk about those images, and begin the dialogue then of what happened in that time period. That's how I've addressed that to a number of people that question it. And you guys don't ever run into people?
I take them to the LROC website.
Which has those?
So I work for the Lunar Reconnaissance Orbiter camera team that takes those pictures, right? And I actually had a slide deck with the images of the landing sites that didn't make it into our slide deck. So they exist. I can show them to you. But you can also Google it, and it will turn up the correct images. But yeah, I usually just take them to the images, but there's also a very good, easy argument for the samples, right? You can't make these samples on Earth. They just don't happen. Some of the minerals are similar, but the rocks themselves do not form here on Earth in the same way. So you can see that in the rock samples. And Sonia can probably speak to that.
Yeah, I mean, if you look at a moon rock under a microscope, you'll see that there are some minerals that are different. On Earth, we have free oxygen floating around in our atmosphere. And oxygen likes to react with iron, so on Earth, we always have iron oxides. And on the Moon, there's none of that, so it's just metal. So immediately, when you look at a moon rock under a microscope, you can say, this is not from here. We don't have free just metallic iron in basaltic lava rocks on Earth. It just doesn't happen. So from my point of view, it's it's clear that they're not from Earth, no matter what, from just looking at samples.
Any others? All right. Okay, from Twitter. From Twitter. How has studying the moon and other planetary bodies helped us better understand the Earth that we wouldn't have known otherwise? Now, to me, this is enormously important. I mean, to me, we are so lucky to have Venus and Earth, planets to compare, terrestrial planets. And we know from lunar material and other material that, our solar system came together 4.6 billion years ago, and they have all evolved. And so what's happened on Venus can happen on Earth. What's happened on Mars can happen on Earth in many different ways. So comparing other planets really tells us a lot about how we've evolved and potentially how we're going to continue to evolve and what will happen to us.
So I think that by studying the other planets, it's really important for our ability to understand the Earth. And part of that comes from the same physics, the same chemistry operate throughout the universe. But clearly there are different outcomes when we look at the different planets in our solar system. And so this is a real opportunity because it allows us to understand how those processes work in different environments. And so, for example, Jim, you were talking about how Venus and Earth have had very different outcomes. Venus is this extraordinarily hot greenhouse planet. It has undergone a massive amount of change at its surface and is a relatively young planet at its surface. But I think one of the things that's really important and is one of the fundamental questions in Earth science is, why do we have plate tectonics? And so we can start to look at other planets to help us to understand that question. And what's really interesting is that Mercury doesn't have plate tectonics, Mars doesn't have plate tectonics, Venus doesn't probably have plate tectonics. And so now we can start to question, what is it that's special about here on Earth? So we can start to ask those kinds of questions.
Yeah, right.
And systematically start answering it.
Yes.
My favorite angle on this is the bombardment record. So we mentioned that the history of the early solar system is preserved on the lunar surface. And that is what makes it unique, right? Because that is not recorded on Earth. We do have plate tectonics, which destroys everything. We have erosion, it destroys everything. Mars is eroded. Mercury's covered in lava. Venus is covered in lava, and a horrible atmosphere gets in the way of everything. So the moon really is a really unique place to see this. So the bombardment record, these large impacts that you can see with the naked eye, those are preserved there where they are not otherwise preserved. And so this actually feeds into some critical important questions about Earth. For example, when did life evolve? Could it have evolved when we think it did? Because if you had a large flux of impactors and you just had impacts all the time, like Sonia mentioned about the dinosaurs, if you had all these impacts going on, you couldn't evolve life. It had to happen either way before this massive influx, or it had to have happened after. And so that gives us some clues as to where else to look for life in terms of the timescales over which it evolves, but also just on our own planet. What piece of history are we talking about? Is life a relatively new thing, or is it way older? We don't know. And so the moon is one of the keys to unlocking that question.
Mm-hmm. Sean?
The hypothesis that it was an asteroid impact that killed the dinosaurs 66 million years ago would not have been accepted without the lunar program. We would not have appreciated, and terrestrial geologists simply dismissed as unimportant impact cratering as part of a critical geological process on this planet. And as we've mentioned earlier, the earliest history of the solar system is not preserved in the rock record on Earth. We have no rocks that date from the first 500 million years of Earth history. So as well as we can study our own planet, the earliest chapters are not available to us. And it took the lunar missions, it took the exploration of the other planets to reveal to us how chaotic and how disruptive the early history of the solar system was, how giant impacts were common, how the growth of the planets themselves was a long, drawn-out process involving multiple collisions and gravitational interactions, and how and this benefited from the study of planets around other stars, how even the positions of the major planets around the sun changed over the early history of the solar system, and that impacted all of the other planets as well. And so the time that is lost to us on Earth is found on the moon and on the other planets and in the dynamics of the solar system, and tells us something about the really challenging environment that our planet first faced. And the contrast between Venus, Earth, and Mars in terms of starting conditions that are more nearly comparable, and yet outcomes today that are so different, with a runaway greenhouse on Venus and an atmosphere on Mars that was largely lost after the planet lost its magnetic field, leaving a cold, arid body as our neighbor outward from the sun. So those are important lessons for the sensitivity of the evolution of our own planet and our own climate to small differences in conditions, distance from the sun, differences in atmospheric composition, and differences in the history of the magnetic field, and how they can have profound consequences for the difference in surface outcomes.
Sonia.
I think because the moon is such a well-preserved body, like the crust basically holds on to what was going on geologically at the beginning of the solar system, it's great for understanding what the Earth was like early on, and not just from an impact standpoint, but also from a planetary evolution standpoint. At some point, plate tectonics turned on, but the Earth may not have started right off the bat with plate tectonics. The Earth might have more resembled, Mercury and Mars and the moon at the beginning, with a solid outer crust and then a mantle underneath it that was, convecting and doing things and creating volcanism. And the moon is a cool laboratory for understanding, possible outcomes for bodies that have a solid outer shell. You have this crazy asymmetry on the moon. We're used to seeing the side that we look at with like the white crust and the dark lava flows, but what you might not know is if you look at the other side of the moon, it doesn't look like that. There are big impact basins on the far side of the moon, but they're not as big as on the near side because they evolved in a different thermal regime. And they're also not filled with as much lava, and you don't have these dark regions on the far side of the moon. And so it tells you that in these planetary bodies that have a lid crust, you might have some weird magmatism happening on the interior of the body. And we see asymmetries in other planetary bodies as well. Mars has a crustal asymmetry that may be from a giant impact, and may be from some internal process. All these hypotheses are raging, but I think the moon is a good example of that, of what might have happened before the Earth was as it is today.
Yeah, this is a very important topic, and we can spend a whole several hours on it, I'm sure. So let's go to another question from the audience. Who made the lunar laser light reflector, and what have we learned from those flashing laser lights coming back to us from the moon?
I don't remember who made the
They make them now.
The corner reflectors, I don't
the corner
remember either.
reflectors. I don't remember who.
Okay,
created
so
the
that's
first
lost
one.
in history.
Yes. so there are new ones.
But probably
Someone knows.
could
Chapter we didn't read,
could be found. But
So-
what are we learning from those?
So retroreflectors were left by several of the Apollo missions. And so what we learn is to extraordinary precision between my fingers, the rotation rate and the distance to the moon. And so by measuring that over many, many, many years, we can understand essentially how is, imagine spinning an egg, whether it's hard-boiled or one that isn't, and how the different of that is tells us about what the interior of that egg looks like. Is it hard-boiled or is it not? And so that's one of the main questions, is trying to understand in the interior, what is it like? And so coming back to the question that, that Sonia has talked about a lot, what does the core of the moon look like? Is it still liquid today? That's one of the fundamental questions. And so those are the kinds of things that we're using. We're trying to understand, actually, in many ways, the deepest interior through measurements that are still made today.
Yeah. Okay, but the distance. We do it every year for 50 years. Didn't we get it right the first time?
That doesn't mean it's not changing.
What's happening? So the moon is moving away
Away
from
from
the
the
Earth.
moon.
Yeah, about 1.5 inches a year. Wow.
And so that tells us about the tidal interaction between the Earth and the moon. And so that's an important way of understanding that interaction of the Earth and moon system.
Okay. All right, another question. If the moon doesn't show signs of contraction, okay, while it cooled, as Mercury did, is it possible the moon is hollow? All right.
No.
Okay.
There are signs of contraction.
Well, you talked about the, okay, so let's tease this out a little bit. So, I saw the ringing of the moon, and that ringing is in the crust. Okay, so there are seismic impacts, and it just really rings the crust. Are there traces from the seismic measurement that are interior of that
Yes.
go through the mantle, that
Yes.
go down to the core?
Yes.
That's the dead
This
giveaway.
is an example of why you archive data.
Yes.
The Apollo seismic experiment ran from Apollo 12 until the end of fiscal year 1977. So it collected about 8 years of data on moonquakes, shallow and deep, and on meteoroid impacts during that period that were carefully archived by the Massive Seismic Experiment team, and that NASA preserved the data. And decades later, in the late 1990s and early in this century, seismologists returned to those data with new techniques that have been developed since the Apollo era, and were able to see features in the seismograms and in combinations of seismograms that they hadn't seen before. So in particular, they were able to see reflections from the lunar core. They were able to see evidence that the core is divided into a fluid outer part and a solid inner part, and to see a distinctive layer above the outer core that may be close to partial melting of the silicate rocks. But they did that with waves that traveled all the way down to the center of the moon and were reflected back up.
Yeah, they had to find them in that data. That's the tough part. Yeah, so that's the science.
But that rules
then.
out a hollow moon.
Yeah, but okay, you could have started out with that hypothesis. That's not that's an important way to look at it. All right, would Earth exist, meaning human life on Earth, without the moon? This is a really good question.
It's a very good question.
Yes, they all have been, by the way.
I can partially answer that. The direct answer is difficult. But there's an interesting contrast between the Earth and Mars in the history of climate over millions of years. Mars does not have a major moon. It's got 2 little moons that were probably captured. It doesn't have a major moon. And as a result, the position of the spin axis relative to its orbit plane changes drastically over timescales of millions of years. The angle between the perpendicular to the normal plane and the spin axis is called the obliquity. And the obliquity on Mars varies all over the place. It's been known for several decades. And as a result, the climate, including the location of ice and CO2 ice on Mars, has varied enormously with latitude. There's probably ices left over near the equator from times when the spin axis was pointing way different from the perpendicular to the orbital plane. The Earth, as you know, the reason we have seasons is there's a tilt to the spin axis, a pretty fixed obliquity, about 23 degrees. And that obliquity is stabilized by our moon. And the moon helps to keep the Earth's orientation in space with the spin axis having the characteristics it does today. So
Yeah,
at
so
least
today-
one of the challenges to life, which is a drastically
Yeah,
changing
right.
climate,
It's climate.
would be very different without the moon. Now, that
Very
doesn't
different,
completely
very
answer the
different,
question,
yeah.
but it's part of the
Yeah.
answer.
So right now it's 23.5 degrees, and it can be 22 degrees and 24 degrees. So
Yeah.
it hardly moves, and even that produces enormous changes in our climate.
It does.
So if you can imagine it laying over 45 degrees, the change in civilizations and migrations and everything else you'd have to do to be able to survive that. So indeed, the moon provides that, and that has really been an important stabilization for us. Okay, this is another one I like. If you had a blank check, okay, scientists, what instruments would you send to the moon on the very next mission?
Libs. I want something that could derive the radiometric age of rocks so that we wouldn't have to bring them back to Earth. You could just sort of wander around the surface and figure out the ages of things as you went along. Because for sample return, you're limited by mass, right? Because it's hard to get stuff back and get there. And so if you had an instrument on site that could do that, and there are instruments like this under development.
Yes, they are.
But it's like trying to put a laboratory the size of this room into a tiny little box. So it's very challenging. But if you could do that, then you could do a whole lot with the chronology, and you could learn a lot about the history of the solar system purely by roaming around the surface.
That's right.
I think we have to send back seismometers.
Yes, so seismometers that we put there had some limitations.
They had some limitations. And one of those limitations was, as Sean mentioned, the duration in which they were operated by NASA on the surface of the moon. And another one had to do with the locations. They were all on the near side.
Yes.
And so that limited our ability to understand where earthquakes were throughout the moon, and limited our ability to understand the structure of the moon. One of the understanding the deepest interior is difficult. And so we need more data in order to understand really how big is that core. We know that it's there now due to analyzing those archived data, but there are questions in the scientific field about exactly how big it is, exactly how big the solid portion of that is. And these are things that are really important for being able to understand the history of that core that can lead to the history of the magnetic field.
Yeah. Also, it fits into the theories in terms of, when Theia, as it was called, hit that proto-Earth, Theia lost its core to the Earth, and it's only the remnants of that came together and created a core. So one would expect that core to be smaller than if it had accreted on its own without an impact.
And it is quite small.
Yeah, and that's what, at least we initially think that. Yeah, that's right. Sean?
If I had a blank checkbook, I
Yeah.
probably wouldn't go to the moon next.
But I would take advantage of the latest discoveries in the pole.
Yeah.
I would want to go and core the ice. We
Yeah.
know there's
Yeah.
between 100 to 200 million tons of water ice in those permanently shadowed craters. And that accumulated over time, over different epochs, when the moon had a magnetic field and when it didn't. And so we want to understand that, and the only way to do it is to get a core and be able to look at it. And that's going to be really tough, to go into a place that's dark, because the ice is there, and locate what you want and get that core and come
Hey,
back.
give me your blank check. I'll do it.
Sonia.
I really like the idea of drilling deeply into the moon. So I think one thing that I would do is I would have a device that could drill like more than 1 kilometer down into the surface, and I'd probably go into either a stack of lava flows, or I would drill directly into the impact melt sheet inside a basin. So like you have a big impact and it melted all of these rocks and they cool down again. And what's kind of cool about big magmatic bodies that cooled slowly on Earth is they sort of separate into layers, and some layers are full of like ore minerals and stuff like that. And maybe something similar happened on the moon. Some of the largest magnetic signatures, the most powerful fields on the moon, are measured at impact crater locations. And I'd like to figure out, like, where in the crater is that coming from? It's this big mystery right now. And so therefore, that's what I would do.
Okay, all right, good. All right, next question. What are some of the exciting technological advances that you think will revolutionize space exploration over the next several decades?
I'd just say miniaturization.
Yes, CubeSats,
Yeah, like
nanosatellites.
we can make everything smaller now. We can send 100 shoebox-sized probes crashing towards the moon and making every type of like geophysical remote sensing measurement on the way down. Like you could learn so much from that. Or just putting small instruments on a rover and actually dating moon rocks at the surface would be incredibly useful. And just the fact that we can do all of these, small lab on a rover, or just from the CubeSats, you can learn so much from that.
Enhances our remote sensing.
Yeah.
Our ability to communicate, we're moving towards, instead of radio communication, to laser communication, and so we can bring back an enormous amount of data. In planetary science, we're very limited in terms of the amount of data we can get back, because the further you are away, the lower the data rate is. That's just one of the physical laws that we have to worry about, unless you change the wavelength and then up your game. So now those kind of technologies are right around the corner. Also, the ability to go from point A to point B with ion engines, like we did with a mission called Dawn. Dawn was a spectacular, it's like the Star Trek impulse engines. These are them, okay? So we were able to just saddle up to a huge asteroid called Vesta, get it right into orbit. Now, when we approached it, we ended up approaching it about the speed of an airplane landing on a runway, okay? And that's what that ion engine enabled us to do. And then we broke orbit and went out to another one, which was Vesta. But those engines are getting better and better, and that will actually open up many more objects for us to be able to get to and really study and analyze. Any others, Roger?
Steve?
Well, you look like you were going to say something.
Yes. So one of the things that I think is exciting, that I think is already happening, is drone technology. And so NASA just selected a mission that's going to use that technology to fly in the atmosphere of Titan and to be able to explore its surface. And so I think the ability to take that sort of technology and be able to explore greater distances, to be able to choose where you're going to explore as you are exploring, I think is exceptionally exciting. And it's this great merger of aero and space in what we do. And I think there are other places that we can imagine doing things that are more of flight, whether it is at Venus or whether we can someday, with that blank check, be able to do those sort of things in the top atmospheres of the larger planets in our solar system. And so
Well,
I think
speaking of flight, okay, so we've already cashed this check. We have a helicopter on a mission going to Mars. We're going to launch it in July. It's a rover. Looks like Curiosity. And it is underneath the belly pan of the rover. So once it lands, that helicopter will be dropped. We'll drive away. We'll start it up, and it will have a GoPro camera on it, and it will look at its path ahead of the rover and set down, radio back that information for the rover to make decisions on how it will move forward. And this, I think, is just the start of how we might be able to use these kind of new vehicles. And because Mars has an atmosphere, and although it's very thin, we're able actually to navigate in it. And those planets that have atmospheres are next on our list. So it's really exciting time. So this will have to end our little overview, our panel. Let me thank everyone. It's been a delight. Thank you very much. Thank you so much for coming. I have a few minutes. I've been allowed a few minutes to wrap up. And so let me mention a couple things about what's coming up. You know, we're going to be going back to the moon. Actually, we like to call it going forward to the moon, with not only many more landed systems over the next several years, but also the plans are to have humans on the surface of the moon by 2024. And so by 2024, you will witness, you know, the youngsters in the audience that hadn't seen the original, any of the landings will have the opportunity to live what we lived in our young careers. And I got to tell you, I don't think you'll be prepared to see what will happen. It will be so exciting. We're going to have the first woman and the next man stepping on the surface of the moon in the southern polar region. And so unlike what we see with the Apollos, with short shadows because the sun is nearly overhead, we're going to have some eerie views with very long shadows and a whole host of new science things that we're going to do. So this is a tremendously exciting era coming up. And so once again, thanks so much for coming, allowing us to talk about our exciting first set of missions that have gone to the moon, both in human exploration, but our robotic missions. But let me tell you, that is only the start of what we have planned for the next decade. Thank you very much. Thank you, Penny.